in this module we will discuss solution of undamped free vibration. So this undamped free vibration means, so free vibration means where force is 0. So there is no externally applied force, and then when we call it as undamped, so that means damping is 0. So undamped free vibration. So the outline of this discussion or the module is undamped free vibration, and then how to find a solution of this undamped free vibration, and then one example problem will solve in this module. So this is a general dynamic equilibrium equation or equation of motion, we can call it as. So the equation of motion of a vibrating system, so the free vibration and forced vibration. Free vibration means where force is equal to 0, and forced vibration means force is present, it is not 0. And in that 4 cases can be formed. One is undamped free vibration. So undamped free vibration, damped free vibration, undamped forced vibration, and damped forced vibration. So undamped free vibration means damping is 0, force is 0. Damped free vibration means damping is present but force is 0. Undamped forced vibration means damping is 0 but force is present. Damped forced vibration means damping is present and also force is present. So these 4 cases we will discuss, out of which we are discussing this first case, that is undamped free vibration. So how does equation of motion look like? So it looks like this: mu double dot plus ku is equal to 0, where damping term is removed from this one and force term is removed from this one. As you can see from this picture, so force is not there and damping is not there. So when force is not there, how the system is oscillating? So system will oscillate with initial disturbance. So that initial disturbance can be in the form of initial displacement, like this initial displacement, it oscillates, or initial velocity which is applied in the form of impulse or velocity. So this is initial velocity, or both initial displacement along with initial velocity, like that. So if we supply initial disturbance, either initial displacement or initial velocity or both, so system will set to oscillate. Then how do we find the solution of this equation of equilibrium, that is mu double dot plus ku is equal to 0. So for that we will discuss here. So how to form a solution. So this is mu double dot plus ku is equal to 0. So this is a basic equation of motion. So we want solution, we are interested in the solution, which is u. So u, we are assuming it as u is equal to e to the power of st is a possible solution. So this we are assuming that e to the power of st is a possible solution. So this is a usual solution taken for simple harmonic motion problems. So if u is equal to e to the power of st is a solution, then its derivative, that is u dot, that is velocity. So if we differentiate this one, we get s multiplied by e to the power of st, and then if we double differentiate the same, then we get s square e to the power of st. So we substitute u and u double dot in the original equation. So if we substitute that, as you can see here, so u double dot as e to the power s square e to the power of st we have substituted, and then u as e to the power of st we have substituted. So that is mu double dot plus ku is equal to 0. So in this we can take e to the power of st as common, and m s square plus k in bracket multiply by e to the power of st is equal to 0. So from this equation we can clearly see that for this equation to become 0, either first term should be 0 or second term should be 0, mathematically speaking. So if second term is 0, so that means what? Second term is nothing but the assumed solution. So we cannot make this second term 0. So if second term is 0, that will become a trivial solution. Trivial solution. So for non-trivial solution, this e to the power of st, which is the assumed displacement response, it cannot be 0. So that means what? If e to the power of st cannot be 0, so then that means bracket term should be equal to 0. So that is ms square plus k is equal to 0. So this bracket term should be equal to 0. So if this bracket term is 0, then what is going to happen? Let's see in the next slide. Yeah. So if that bracket term is equal to 0, so which is ms square plus k is equal to 0. So it means s square is equal to minus k by m, and then s will become under root minus k by m. So this under root minus k by m, if we take out this minus under root I, under root minus 1 multiply by under root k by m, to separately with a symbol plus or minus, because it is in the inside the square root, it is coming out. So then we can have two answers to this one, S1 and S2. So that S1 is with plus symbol and S2 is with minus symbol, and then this under root k by m can be represented as omega n, which is called natural frequency of the system. Natural frequency of the system. So then that gives us two roots to this equation, that is S1 is equal to plus I omega n and S2 is equal to minus I omega n. So these two values are there, S1 and S2. So now upon substituting this S1 and S2 in the back in the equations, so we get this. So ut a1 e to the power of plus I omega n and a2 e to the power of minus I omega n. So this is a form of solution of linear differential equations with constant coefficients, linear differential equation with constant coefficients. So this is a solution form of that. So this is complicated, so we need simplified solution. So there we use the trigonometrical functions, which is cos x can be represented as in the form of exponential terms, that is e to the power of ix plus e to the power of minus ix by 2, and sin x can be represented as e to the power of ix minus e to the power of minus ix by 2. So this cos x and sin x along with this exponential terms can be rearranged, and this solution can be written in the form of c1 cos omega n t plus c2 sin omega n t. So in this equation, so we have two constants c1 and c2. So we need to get rid of these constants c1 and c2 for getting a complete solution. So this c1 and c2 can be calculated or can be found out by using initial conditions, and we have two initial conditions. So that is at time t is equal to 0, what is the status of displacement? At time t is equal to 0, what is the status of velocity? So at time t is equal to 0, what is displacement? At time t is equal to 0, what is velocity? So this is something like this. So time u at u is equal to 0 is first initial condition, and u dot at time t is equal to 0 is a second initial condition. So if we substitute these initial conditions in the equation, we will get c1 and c2. It's something like if we substitute say u0. So let initial condition, that is u displacement at time t is equal to 0 is 0. So if we substitute this, so what is going to happen is time t is equal to 0, so cos 0 and sin 0. So sin 0 is 0, cos 0 is 1. So if sin 0 is, let me write here, say u of 0 is equal to c1 multiplied by cos omega n into 0 plus c2 sin omega n into 0. So this gives us sin 0 is 0. So this entire term goes to 0, and cos 0 is 1. So that gives us c1 is equal to u0. So this c1 as a constant is evaluated. Now we need c2. So c2 is having a term as of like in second initial condition is having u dot. So but we have solution u. So we need to do the differentiation of this solution. So u dot of t is equal to c1 term will remain like that. Then differentiation of cos will be minus omega n sin omega n t plus differentiation of the second term, that is c2 will remain like that, omega n cos omega n t. Now we need to apply the second initial condition in this one. So that second initial condition is u dot 0. So u dot 0 is equal to 0 if we are using, then c like omega c1 into omega n with minus symbol, and then sine omega n 0 plus c2 omega n cos omega n into 0. So again here you can see sine 0 is 0, so this entire term goes to 0, cos 0 is 1. So that means what? U dot 0 is equal to c2 omega n. This implies c2 is equal to u dot divided by omega n. So we got c1 constant and we got c2 constant and c1 constant. So if we substitute this c1 and c2 constants in the original equation, that is a solution, so we get this. So from this you can see this is a solution of undamped free vibrations. So in this u0 is the initial displacement and u dot 0 is the initial velocity. So from this equation we can clearly see that if we supply initial displacement or initial velocity or both, then only undamped free vibration, then only there will be oscillation in the system. Otherwise, if initial displacement is 0 and initial velocity is 0, system cannot oscillate. System will be in the static position only. So now this slide shows the overall summary of undamped free vibration. So this is a system where damping is 0 and force is 0. Then equation of equilibrium is mu double dot plus ku is equal to 0. If we divide this equation by m, so that gives us u double dot plus k by m, we have already discussed it, that is equal to frequency omega n. Omega n is equal to under root k by m. So if k by m is nothing but omega n square. So this is a equation of motion. The solution of equation of motion is this. Solution of equation of motion is u0 cos omega n t plus u dot 0 by omega n into sin omega n t. So in this u0 is initial displacement, u dot 0 is initial velocity, and natural frequency which is omega n is equal to under root k by m. Yeah, again initial displacement, as you can see here, at time t is equal to 0, this is the time scale. At time t is equal to 0, initial displacement is having some value, it is non-zero value. Okay, some value is there, but initial velocity is, that is tangent is horizontal to the x-axis, that means initial velocity is 0, initial displacement is non-zero. In the second case, initial velocity is present, initial displacement is 0 and initial velocity is non-zero. And here in third case, initial displacement is there, also initial velocity is. So these three cases are there: initial displacement, initial velocity and initial displacement along with initial velocity, 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 with initial. Now let's try to find out the system parameters, so which are very much essential in linear single degree of freedom system for finding the solution. So the two important system parameters in undamped free vibration are mass and stiffness. Mass and stiffness, that is m and k. So mass and stiffness. So if we look at this structure, a slab supported on 4 columns. So thickness of the slab is given is 120 millimeter thick and column size is 230 by 300. So 230 on one side, 300 on the other side, 230 by 300 mm column size, and the grade of concrete used as M20 grade concrete, material grade, and height given as 3 meters. So a note is given that all the columns are fixed at base, fixity is there here, fixed at base, slab is rigid in its plane. So there are no internal deformations in the slab, internal deformations are not considered in the slab. So then how do we calculate the system parameters? So first of all we need to calculate mass of the slab. For calculating mass of the slab, we calculate the weight of the slab first. So weight of the slab is, we can get it through volume multiplied by weight density. So volume is 3 meters by 3 meters by this 120 mm thick. So this is the slab volume of the slab concrete, multiply by weight density. So since this is reinforced cement concrete slab, so 25 kilonewton per meter cube is a weight density. So that gives us 27 kilonewton as a weight of the slab. So mass of the slab is equal to weight divided by gravity. So gravity value we are taking it as 9.81 meter per second square, and 27 kilonewton, that is multiplied by 1000, we get 27,000 newton divided by 9.81. So we get 2750 kg is a mass of the system. So this is the first parameter. Now we need to find out second parameter, stiffness. One note that columns are assumed as massless. So usually columns contribute to the slab mass, but in this case we are ignoring the mass of the columns. Columns are contributing only for stiffness. So how to calculate the stiffness of the column? So first of all, we find out the modulus of elasticity of the material, column material, that are the concrete material. Since concrete material is given as M20 grade concrete, so according to IS 456 2000, we calculate modulus of elasticity as 5000 under root FCK, so which is 22,360 Newton per millimeter square, that is modulus of elasticity. And then moment of inertia of column section I is 300 into 230 cube divided by 12. This is along one direction. And lateral stiffness, say one column. So if we take stiffness of this column along this direction, if it is moving like this in this direction, so 1 unit. So this we have already discussed in detail. So lateral stiffness of this can be quantified like K1 is equal to 12 EI by H cube. In this one, E is the modulus of elasticity of the concrete material, I is the moment of inertia along the direction of motion, and H is the height of the column. H is the height of the column. So like that we are evaluating, because 4 columns are present in x direction, 4 columns are resisting the opposing the motion along x direction, again 4 columns are opposing the motion along y direction. So what we do is, when we are calculating along x direction, so we will take moment of inertia accordingly in that direction. So if you look at this one, 4 times multiply by 12 EI by L cube. L is the length of the column or height of the column. So this is stiffness of one column multiply by 4 columns. So E is modulus of elasticity, that's 22,360 multiply by I along one direction. So 3.04 into 10 to the power of 8 divided by height is 3 meters. So 3000 mm cube. So we get 12.08 into 10 to the power of 3 kilonewton per meter, that is lateral stiffness along x direction. And then moment of inertia of column section along y direction is obtained as 5.18 into 10 to the power of 8 mm power 4. And accordingly, if we calculate stiffness, so that is 4 times 12 EI by L cube, we get 20.59 into 10 to the power of 3. So in this we can observe one thing is, here it looks like, you can see column size is 230 by 300. So columns are 300 millimeter depth along y direction, and the size of the column along x direction is 230. So that means what? Along x direction structure is little flexible, and along y direction structure is little stiff. This is a relative stiffness. So along x direction it is flexible relatively, along y direction it is stiffer relatively. So the same thing we can see in the stiffness also. So along x direction we are getting stiffness, that is resistance to deformation, as 12.08 into 10 to the power of 3 kilonewton per meter, and along y direction 20.59 into 10 to the power of 3 kilonewton per meter along y direction. So this is a stiffness calculation along x direction and y direction. So that completes the calculation of stiffness along x direction, along y direction. So if structure is vibrating along x direction, we can use mass as well as stiffness along x direction. If structure is oscillating along y direction, then we can use mass and stiffness along y direction. In this example, we will learn how to evaluate natural frequency of the system where parameters of the system are given to us. Like question reads like this: the roof of one-story building has mass 2000 kg. Mass is one parameter which is given already, 2000 kg. All the columns supporting the roof together offer a lateral stiffness of 13,000 Newton per meter. So this 30 kilonewton per meter or 30,000 Newton per meter, this is second parameter. So mass is given to us and stiffness is given to us. So we need to find out natural period of the building. So natural period of the building and natural frequency of the building are related in this form: omega n is equal to 2 pi f. So this frequency is number of cycles per second. So in 1 second, how many cycles are taking place, that is represented by frequency f, and natural period is time taken for one to and fro or one full cycle. So they are related. F is equal to 1 by t or t is equal to 1 by f. So in this relationship, so omega n is equal to 2 pi f, we can also write this as omega n is equal to 2 pi by t, or t is equal to 2 pi by omega n, so Tn. So we know how to calculate omega n, which is under root k by m. So k we know 30,000 Newton per meter, and then m is 2000 kg, so we get 3.87 radians per second. So this is circular frequency. So this 3.87, 2 pi divided by 3.87, we get 1.62 seconds. So natural period of the system is 1.62 seconds. So that's what is asked to calculate. So system parameters are mass and stiffness are essential for finding natural parameters or natural characteristics of the vibrating system, that is natural frequency or natural period.